Welcome to my presentation. As a presentation, I want to share with you a new network that is SBCFormer, a lightweight network capable of full-size ImageNet classification at 1 FPS on single-board computers. First, I want to start my presentation from one question, that is, which applications require running deep neural networks on low-end processors. There are three real-world typical applications. One is architecture automation. The second is intelligence animal repellent. And the third is the AI for fishery. For example, in AI for fishery, the deep neural networks are usually used to identify fish, detect fish, and sometimes they are used to retract fish. But recently, there are less efficient models designed for those lower-end processors. And numerous designs of models are proposed for the smartphone. They regard smartphone as their target devices. While smartphones are still powerful, for example, the iPhone 12 is much powerful than the Raspberry Pi 4 mobile. In this case, what will happen if these efficient models are deployed on low-end processors? Can this still work well under the constraint source situation? Usually, lower-end processors has limited computing capability, less storage capacity, and constrained power budget. As true in Figure 1, efficient neural networks designed for mobile devices and a smartphone perform worse on lower-end processors in terms of between computational efficiency and inference accuracy. After doing independent experiments, we found the following three reasons are primarily responsible for the inefficiency of models running on lower-end processors. First is the convolution typically has large method-matched multiplication and require a complex memory access planner, resulting in higher I/O throughput and higher latency, especially for convolution with large kernel size. And the second is the transformer self-attention carries a quadratic computational complexity in terms of the number of tokens. The third is attention mechanism that typically used to unleash the upper hybrid models lead to suboptimal inference accuracy, as it gives up one crucial property of AIT, that is aggregating global information from input images. So, what kind of models can overcome those challenges and achieve better trade-off between computational efficiency and inference accuracy? One possible solution is to design our hourglass architecture. It motivates us to design the SBC model for the low-range processors. Our model contains two key parts. One is the SBCFormer block. It is an hourglass architecture. It with two streams. The first stream shrinks the input feature into a small size and apply the attention to reduce the number of tokens. And the second stream access passes through to return local information from the input images. Finally, both streams carry and generate one feature map, enriched with both local and global information. Through doing this, SBCFormer can preserve local information and optimize attention computation. In modified attention mechanism, a tuple of a binomialized depth-wise convolution or activation function is applied to B. It efficiently enhances the representational power by improving the aggregation of the spatial information in the input feature map. The ablation experiment as shown in the table 1 confirm the efficacy of the proposed two blocks. To identify our model performance, we do experiments on 3 platforms, that is, our CPU, Intel CPU, and NVIDIA CPU, to calculate the latency performance. We perform 300 inference and report the average latency in seconds on each platform. The results on ImageNet 1 case show that SBCFormer achieves the highest trade-off between accuracy and inference latency on low-end ARM CPU. Specifically, it achieves an 8% top 1 accuracy with only 0.93 seconds on ARM CPU. Moreover, our model can also work well on dense vision tasks as shown in table 3. Finally, is the conclusion. Our gloss architecture with two streams have superior advantages for applications on low-end processors. Our proposed SBCFormer achieves the highest trade-off between accuracy and speed on low-end CPU. If you want to check our code in detail, you can see the following link. Thank you.